Okay, in our previous lecture, we defined the Cauchy stress, and we also defined the Cauchy stress formula. And if you remember, I'm now drawing this all in more explicit detail. We had this is your stress cube, and you can look at the 6 unique stresses, normal stresses on the 3 normal planes, and then shear stresses on the face of those planes in the other 2 coordinate directions. And we could write that as a matrix. So here's sigma, the stress matrix, as a symmetric 3 by 3 matrix, sigma 1, 1, 1, 2, 1, 3, and then 2, 2, 3, 3, and 2, 3 being our unique stresses. So then the next question that arises is, what is the extreme value of the normal stress? If we have some arbitrary state of stress where, let's say, the stress tensor is fully populated, not in like just a simple uniaxial case, and let's say we know that there's a material has a particular strength, that is, it can reach a certain stress, and then beyond that stress, failure happens, whether it's fracture or yield or whatever. Sometimes we want to know what's the extreme value of the normal stress. So I've drawn a little picture for you here. So asking the question, what's the extreme values of the normal stress? And I want to remind you, here's our plane of interest, that's defined by the unit normal n. So I've drawn that. It's of course at a right angle to the plane. And the normal stress on that plane is the stress that's directly orthogonal to the plane, or that is in line with the unit normal n. And then I'm also showing you in this case, the traction vector t that would produce that normal stress sigma n. So what we're trying to ask is what if in all that stress tensor, if we can pick any plane that we want to figure out which plane it is that gives us the maximum or the minimum or normal stress. And I'm going to expand that a little bit to say what we really want is a stationary point. So we would admit saddle points as well in that. So the question we want to ask is, what vector n, right, some 3-dimensional vector in space, makes sigma n an extreme value? And I'm going to be a little bit more formal and say a stationary point so that we admit saddle points too. Okay, that's the question that we're trying to answer. So the first thing we want to be able to talk to is just answering, if I pick n, what's the normal stress on it, right? So the first question we want to answer is, what is sigma n given some stress tensor sigma and unit normal n? Okay. So we can write sigma n, and let's just scroll back up really quick to see what that picture looked like. What sigma n is just the component of the traction vector that's in the direction of the unit normal of the plane n. So it's basically just the traction vector dotted with n. So we would write that here as t dot n. Or we could write that in index notation as ti ni. And I'm going to drop the hat over the n. Just remember that it's a unit vector, just for the ease of writing it. Okay? So hopefully that's straightforward. And you know what Ti is, right? From the Cauchy stress formula. So, let's say from the Cauchy stress formula, okay, we can write that Ti is equal to sigma ij nj. Okay, so now we can go ahead and just substitute that into our equation for sigma n and say sigma n is equal to sigma ij nj ni. Or I like to write it for reasons that are not always clear. It's the same I could write it equivalently as ni and j, right? I can move around any of those terms without changing anything about this equation because it's all written in index form. Okay? So that's, hopefully everybody agrees, that's how we would compute the normal stress on any plane. Now what we want to ask is, how do I find the extreme value? So that's, first question was, what is the normal stress? And now how do we find the extreme? Or how do we find the stationary point of sigma n? Well, if I was in class, I would pose this question and I would stand here with in silence until someone told me. But usually when I ask for extreme value, somebody invariably says we take the derivative and set it equal to 0. And that's exactly right. So I'll just say here that it's tempting to say, well, let's take the partial of sigma n with respect to, let's say, nk, and set it equal to 0. That's a good first thought. But we have a constraint. Okay? And that constraint is that n is not free to be anything that it wants. We require that n be a unit vector of 1. And so we could write that just like I've done here, or we could say that n, I should stop using the hats, but n dot n equals 1, or in index notation, that would be ni equals 1. Okay? So that's the constraint that we want to put on it. Hopefully, you now rack your brain thinking, how do I optimize with constraints? And hopefully you dip into your toolbox from Calc 3, and remember we can use something called Lagrange multipliers. So we use Lagrange multipliers to enforce the constraint. Okay, and if you remember, we had to, let's form a new function. So here I'll go ahead and write what I'll call an augmented function. So this is a function that has the constraint built into it. And this time I'll just call it f, and it's going to be some function of n. And it's going to look like sigma n, so just like what we had originally. But now I have the constraint, which we write as lambda, which is the Lagrange multiplier, times the constraint, which we have written such that it always equals 0, right? So if this constraint up here is satisfied, that term should equal 0. So we didn't really do anything except add the term, and we're gonna optimize now with this new variable lambda. So we can optimize, or extremize if you like, by saying that del f del nk is equal to 0, just like we had up here with del sigma n del nk. So that's fine. But we also have to add this new constraint del f del lambda equals 0. And if you go up and just do that in your head, you can see if I take the derivative of the partial of this function f with respect to lambda, sigma n has no lambda dependence, so that goes to 0. This is just a linear term, and we're just left with our constraint. So this basically just gives back the constraint. Okay? Okay, so now we know what we want to optimize. Let's go ahead and write f in index notation to show that it's a little easier that way. So we'll say that then f of n is going to be equal to sigma n, the normal, which we said was sigma ij ni nj, and then minus lambda ni minus 1. Now, taking the derivative of f with respect to sigma or nk, taking the derivative and setting to 0, right? That's how we, hopefully you're familiar with that. Okay, we end up writing partial f partial nk is equal to 0. And that's going to be equal to partial with respect to nk of the first term, which is going to be, I'm going to sigma ij ni nj, minus lambda has no n dependence, so I can pull it outside the differential and write lambda times partial with respect to nk of ni minus 1. Okay? Now let's think about this term. Sigma ij is the matrix representation of the tensor that we've got currently, or whatever it turns out to be, depending on it's fixed in once we've defined the coordinate system. So it doesn't have a dependence on nk, so we can pull it outside and write this as sigma ij times the partial with respect to nk of ni nj minus lambda partial with respect to nk of ni minus 1. Okay? So we just now proceed according to our standard calc rules. So I have the derivative of a product, so I use my product rule. So I end up with partial ni with respect to nk times nj plus partial nj with respect to nk times ni. And then if I come over here, I have this lambda term, and I have partial ni with respect to nk times ni, and I have that actually again, so I just have a 2 there. And then the partial of 1 with respect to nk is of course 0, so I'm left with something like this. Okay, so a couple things I want to point out. Let's look at these terms here. And we've seen something like this when we were talking about the partial of xi with respect to xk. But the components of n are in orthogonal directions. So what that means is that if i is not equal to k, then that partial is 0, and if I is equal to k, then that becomes 1. So we write these, hopefully you realize that then, as the Kronecker delta. That would be delta ik, and this will be delta jk, and this would be delta ik. So we could then go in and go ahead and write, now in simplified form, sigma ij times delta ik nj. And I'm going to actually go ahead and I'm going to distribute the sigma through here. Let me write that out. So this looks like sigma ij, and then I'm going to say plus sigma ij. Oops, sorry. Yeah, that's right. Times delta jk and I minus 2 times lambda times delta ik and I. Don't forget also that this whole term, remember, as I wrote above, is equal to 0. So we're trying to solve for the values of n that make that true. Now we want to make note of something. So I'm going to note and remind you that sigma ij and delta ij are symmetric, right? We already showed that, or at least mentioned that. Okay, and what that means is that sigma ij is equal to sigma ji, and delta ij is equal to delta ji. So then we can write our equation, so partial f with respect to nk is going to be equal to. So now remember from your homework set that whenever I multiply my Kronecker delta times with like an ik, I'm free to exchange indices. So this first term becomes sigma kj times nj, and then this next term becomes plus sigma ik times ni. And then I'm just going to go ahead and leave the other for a minute. Minus 2 lambda delta ik ni. Okay? So, and that member equals 0. All right, so what I'm free to do is, because of this symmetry here, then this term here is equivalent to sigma ki, and this this I, as you'll note, is a dummy index, so I'm free to use whatever letter I want. So I could write it as this whole term, rather, as sigma kj nj. Okay, so that's allowed, and similarly over here, because of the symmetry of the Kronecker delta, this also is the same as saying delta ki times ni. Okay, so if I go ahead now and write this out, and I'm going to go ahead. Looks like I've already used I throughout. I'm going to go ahead and change these j's to i's and these j's to i's, and write then that I have sigma ki ni, right, plus another sigma ki ni minus 2 lambda delta ki ni equals 0. Of course, those just add, and that looks like I can pull the 2 out then and write that this is 2 times sigma ki ni minus lambda delta ki ni equals 0. Now I can divide by 2. 0 divided by 2 is 0, and I can factor out the ni, and I can write this then as sigma ki minus lambda delta ki times ni is equal to 0. Hopefully this becomes a recognizable problem. If I write this, maybe if I write it in matrix form, you'll be more familiar with it. Or what it says is that sigma minus lambda I times n is equal to 0. Okay? Hopefully you recognize this as the classic eigenvalue problem. Okay? So what does this mean? Well, therefore, the values of n of that unit vector that are eigenvalues, eigenvectors rather, so E vectors of sigma are the ones that extremize the normal stress. Okay, so finding the eigenvectors, those are the of sigma. Those are the directions in which the normal stress is maximum or extremized or minimum. Okay, so well, what does that also mean? Well, so when n is an eigenvector, what does that mean? That means that sigma times n is equal to lambda times n. Okay, what is, or we could write this in index notation if you like. That says that sigma ij nj is equal to lambda ni. Right? This is our traction vector Ti, and it says that our traction vector, when n is an eigenvector, then the traction vector of the stress tensor on that plane n gives back some multiple of our unit vector n, which means that our traction vector is in the direction of the unit normal. So the only stress we have on that plane is a normal stress. What does it also mean? It means that lambda is actually, which is the eigenvalue. So lambda is the eigenvalue. And is the magnitude of the normal stress. On the plane defined by n. And I'm going to write this down just because I want you to remember it, but because the traction in the n direction, when n is an eigenvector, is in the direction of n. Okay, what does that mean? It means that this there's no shear component. Okay? All right. So, because there are, hopefully you remember how to compute eigenvectors and eigenvalues, but because a 3x3 matrix matrix has 3 eigenvalues and eigenvectors, we represent the 3 values as the 3 principal stresses. Hopefully you remember a little bit about this from Moore's circle. And we call those lambdas, we just call them sigma 1, sigma 2, and sigma 3. We're not going to show it here, but it can be shown that the corresponding, it can be shown that the eigenvectors corresponding to sigma 1, sigma 2, and sigma 3 are orthonormal. Means that they're orthogonal to each other and actually form basically a coordinate system. So, what that means is it forms, or they form together, a set of principal axes. Such that when sigma is rotated to the to align with the principal axes, okay, and the stress tensor becomes hopefully something that you've seen before that looks like sigma 1, sigma 2, and then sigma 3. Of course, it's symmetric still. Okay?